Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on November 4th, 2025, about 2 days ago. This paper introduces UniPruneBench, a unified benchmark for visual token compression that shows random pruning is a strong baseline, pruning ratio dominates the accuracy trade-off, and OCR tasks are the most vulnerable. The paper is titled, Can Visual Input Be Compressed? A Visual Token Compression Benchmark for Large Multimodal Models. And as we will see later, the system-level insights point to tangible gains for faster, cheaper multimodal inference. Also, the author shared a GitHub repo. You'll find an open-source benchmark wired into VLM-eval kit with ready-to-run scripts for Q.5-VL and Intern-VL3, a methods folder of pruning strategies, monkey patches, and utilities. There's a quick start, accuracy and latency evaluation commands, and a simple registry to add your own pruners. Alright. Figure 1 summarizes the whole setup, and the headline results in one view. Visual token compression means removing or merging image patches so the language model processes fewer tokens, which speeds inference while trying to keep accuracy. The left workflow outlines method categories and the reported metrics, including accuracy, performance drop, total running time, and compression time. The right radar chart compares pruning strategies, and random pruning and div prune stay remarkably close to the uncompressed baseline across many datasets. Well, Figure 2 maps where pruning happens in the pipeline so listeners grasp the design space. The left panel outlines the overall flow from vision input through the tokenizer into the large language model. The middle panel details vision transformer-only methods, showing token merging versus token selection, which either combine similar patches or keep a diverse subset. The right panel illustrates large language model-only methods that drop visual tokens progressively across layers to cut compute. Figure 2 mapped where pruning happens, and Table 1 reports head-to-head results for LLaVA 7B across pruning ratios. The table shows how pruning strategies trade accuracy as visual tokens are reduced. Random performs as a strong baseline, matching or beating several crafted methods at moderate compression. Div prune tends to lead under heavy cuts, while sparse VLM shines with lighter pruning. OCR collapses fastest, whereas instruction following sometimes improves because pruning increases the relative weight of text. Table 1 covered LLaVA results, and Table 2 benchmarks pruning methods on Intern-VL 3.8b to show how accuracy shifts across tasks. Pruning ratio means the share of visual tokens retained, which directly trades speed for accuracy. Random pruning stays competitive, while div prune tends to lead under the heaviest cuts. At moderate retention, vision-side methods often edge out language-side pruning, because vision tokens carry most task signal. Instruction following holds up better than OCR, which drops sharply once tokens are scarce. Table 4 compares running time and overheads, showing how pruning changes end-to-end latency at about 89% pruning on Intern-VL 3.8b. Prefill means the encoder pass that prepares the key value cache before decoding. gprune records the fastest prefill at 167 seconds. It also achieves the lowest total time at 454 seconds. Method overhead remains tiny, with each technique adding under 0.5 seconds, so the gains come from shortening prefill rather than the pruning routine. Wrapping up, 2 takeaways stand out. Random pruning is a tough baseline, and the pruning ratio largely dictates the accuracy-speed trade-off, with OCR the most fragile. The broader implication is clear. UniPruneBench standardizes comparisons and points to practical, system-level speedups for multimodal inference. That is it for this episode of the AI Research Roundup. I am Alex, thanks for listening.